In the previous lectures, we learned about the basics of P, I, and D controllers, namely a proportional control, which was the easiest to implement, followed by proportional plus derivative control, which improved the time response, which also had impact on stability. So we could make an unstable system stable with the help of a proportional plus derivative control, and also has more control over pole locations. Proportional plus integral control, it helps in perfect tracking of constant reference inputs, and also we saw its importance in the rejection of constant disturbance inputs. So largely for second order systems, we saw its impact on stability, control over pole locations, tracking of constant reference inputs, and also constant disturbance. Hello and welcome to this lecture 4 of week 5 of control engineering. In this, we will understand few practical aspects of PID controllers, of what are the difficulties and also other aspects when we go on to implement those. Let us start with a simple proportional control. I take a simple plant, a first order plant of with transfer function 1 over s plus a. For a greater than 0, we say that the system is always stable, and at steady state, the open loop will have a y equal to 0. Through a feedback controller, we are now trying to shift the steady state to y equal to 1. So at steady state, I want y of t to be equal to 1 as limit t equals to infinity. Essentially means that I want to track a reference step. Okay, so we did, with the help of a type 0 system, a little bit of analysis on why a proportional controller is incapable of tracking a step input, largely because it had a finite kp and 1 over 1 plus kp was always positive. Now, suppose the error in this is such that et goes to 0 as t goes to infinity. Right? I'm just assuming that the error in the steady state goes to 0. When the error is 0, we say that y and t are the same for e to be 0, which means y tracks r in the steady state. Okay, this is fine. This is assumption valid. Okay, and as we saw that, entire control architecture is how signals flow through various blocks. Let us look at what is happening in each of these blocks. Okay, if error goes to 0 in the steady state, the input also goes to 0 in the steady state. Let's say the proportionality constant is just reduces this magnitude by 0.5. Okay, so when error is 0, it means that y tracks r as t goes to infinity. This means that the error is 0, therefore the input to the control is 0. But then because the input to the control is 0, if I pump in this reference signal and compute my output, it turns out that y actually becomes 0 as t goes to infinity. So which is a contradiction. What is a contradiction? That I assume that my error goes to 0 in the steady state, which also gives me that my output goes to 0 at steady state if the error goes to 0, largely because of the simple math here. Okay, so if ET was feasible, it would mean that UP goes to 0 because that is the input to the plant as t goes to infinity, and the controller applies no input to the system to maintain the new steady state. We'll keep this sentence in mind. And therefore, the controller must supply some non-zero input to the plant to maintain the output at some non-zero equilibrium. Just if this is 0, this will also be 0, and therefore y will also be 0, largely because of linearity. And therefore, the steady state error cannot be 0 with a proportional controller. Okay, so what happens in this case? So let's say I have a plant of the form 1 over s plus 1. I am tracking, my reference signal is a unit step, and I do all the math. So my error at t equal to 0 becomes 1, and error settles down to 0.1. If the error is 0.1, the output is 0.9, and I have provided an appropriate control input here. So all these signals are in harmony. All these signals are feasible. Okay. So limit t tends to infinity, the input to the plant is one, and because of this dynamics, sorry, the input to the plant is zero point 0.9, the output also becomes zero point 0.9. Okay, so this is good. We understand why a proportional controller cannot uh, steady state error cannot be zero, especially because also because I'm looking at a type zero system here. Okay, what happens when integral control, and we'll kind of also revisit this statement here, right? That the control must supply some non-zero input to the plant to maintain the output at some non-zero equilibrium. Okay, what does the integral control do? So now I have this error, and this E of t gets integrated. So it's like it's kind of getting accumulated, right, over time. This will now generate a steady state input of 1. Now a steady state input of 1 gets my plant also to the steady state value of 1. Okay, so we have already seen this, right? Now I'm looking at a type 0 system where we have seen that the integral, okay, so sorry, we are looking at a type 0 system. We added a controller of the form 1 over S, and we have seen that the use of integral control makes a type 0 system to a type 1 system, and it results in perfect tracking of reference inputs for a first order plant. So the control input now is the integral of this error signal. So errors, you see, I start from here. I build up this area here. Okay, so this kind of adds for some positive value. Then it's the error again goes somewhere here, some negative value, and eventually the overall area when I do the int e of t dt, this becomes a finite value in the steady state. It doesn't go to zero as in this previous case here. Okay, so because of which there is a control input at the steady state which holds the plant to the value 1. Okay, I can do the similar analysis when there is a constant disturbance and how it also rejects the effect of disturbance. A few important observations here is that when the plant has has already an integrator, like we saw in one of the earlier examples, right? 1 over s plus 5 or the sorry s plus 2 was the plant, 5 is the controller. Integral control was not necessary for zero steady state error. However, in that case, there was a constant disturbance because we wanted a controller to have a integrator component instead of the plant for perfectly rejecting disturbances. Okay, and then second thing which we will see here is the integrator wind up phenomena. We'll visit this again after we discuss other aspects. So we'll spend a little more time on this a little later. Let us look at the PD controller. In the last lecture, we saw that PD control not only acts on the error, but also on the rate of the error. And when I say the rate of the error, I have information on how fast the error is changing, and therefore I can act proactively to reduce the effect of the fast changing error. It also improves stability, right? As we are effectively adding a zero to the open loop transfer function. We also discussed that because of the derivative of error, because of the derivative of the error, this controller is anticipatory and also predictive, and this also was seen in its effect was explicitly seen in improved damping of the system, right? Where, so we had a system of the form 1 over j s square plus k, and the derivative control added some damping term here to the overall control, to the closed loop. Okay, so it's interesting to note that just the proportional or derivative control is not sufficient, and both terms are necessary in cases. So we had seen how I started off with a plant of the form s square minus b, adding a proportional controller. Just so if I go through a proportional controller. It only made it marginally stable. I go on to add a derivative component to make it asymptotically stable. Okay, so now look at where each of these terms sits. The KP term sits here, and the KD term sits here, right? So KDS influences the derivative term, influences only the S power 1 term, and this is necessarily for damping injection. And the Kp influences the S power 0 term. This is also looks at the natural frequency, and we also saw how it has impact on the stability. And we need access to both of these terms to have complete control over the pole locations. And pole locations have a direct impact on how my system behaves in terms of its transient response, especially the peak overshoot and the settling time. Okay, what are the practical limitations here? If I just say I have two transfer functions, uh, KD times S and something like this, these are improper transfer functions, which means the number of zeros is greater than the number of poles. Okay, so such systems are non-causal, and why I say non-causal is also because I'm looking at the rate of the error, and in some sense I'm having an anticipatory behavior, which is good, but I cannot realize this controllers in pure form. I cannot build a controller of this form with the help of some general components. Not only that, the derivative also acts, because it acts on the rate of the change of error. Its output is highly susceptible to noise, and noise by itself is not very desirable, and derivative of the noise can make things worse. Okay. So one way to get over this is when a low noise sensor is available for output measurement, I can just put the derivative in the feedback path. Okay, and so in such a way that the noisy reference signals might get filtered in the forward path before encountering the differentiator. Okay, therefore, how do we build a derivative control? So what we see is I cannot realize KD times S physically. And also we saw how this has a blocking effect, right, where the output just goes to zero. So what I do is I like this term, but I add a pole, okay? And this makes the system proper, even though not strictly proper. This is realizable. And if I choose the pole location such that it is very far away from the dominant poles, the effect of this pole is minimal. The further we saw the effect of adding poles onto a system, the further away the pole, the less effect it has on the system. Okay, so now my derivative control is causal, and as p goes further away, we kind of realize our original behavior. The multiplicative term now acts as a low pass filter and eliminates high frequency content in the signal before passing on into the differentiator. Okay, and as p goes to infinity, we have an all pass filter and we get back a pure differentiator. Okay, what about PI controllers? PI controller perfect it provided us with perfect tracking of constant reference input and also helped in disturbance rejection. Of course, sometimes adding an integrator may lead the closed loop system to be unstable. And as you'll shortly see, a big drawback could be the integrator wind-up phenomena, especially when my actuator is subject to saturation. However, how do I get rid of this and practically try to implement this without having to encounter instability issues or even things such as the integrator wind-up? If small steady-state errors are acceptable, for example, if I want my room temperature to be 24 degrees and it's say 23.9 or 23.8 or 24.2, is perfectly acceptable, right? We don't need perfect tracking in those cases. Or 60 kilometers, there is not much difference between 58 and 62. As long as the cameras mounted on the highways want to penalize you for 62 kilometers per hour when the speed limit is 60. Okay, we'll not worry about that, but we will see how to approximate a PI controller now. So again, what I would do is the controller, this is a proportional component, integral component, I have Ki plus Kps over S. Again, what do? I add a pole. Okay, and the P could be very close to the zero. Okay, why is it close to the zero? Is what we will analyze now. Okay, so instead of the pole at the origin and the zero in the left of plane, we now have a pole zero in the left of plane, and the controller is stable. Right, so this is also nice. So I have a pole and a zero which are kind of close to each other. Okay, we'll see what is the effect of this now. What I know is with a PI controller, steady state error. So I have now a type 1 system, sorry, a type 0 system or a first order plant. Okay, and the integrator, adding integrator makes it a type 1 system. My reference is a step, and I know that a type 1 system will track a step with zero steady state error. Okay, let's say if I add now like a pole here, right? Which so this approximation I will now call as a lag compensator. This particular thing is now a lag compensator. Okay, the approximation of a PI controller is a lag compensator. What happens to the steady state error? The steady state error now just becomes, I do all the math, I have 1 over 1 plus k, z over p. Earlier, p was 0, so this became, the steady state error became 0. The steady state error will not be 0 with the help of a lag compensator, but then I can appropriately choose the location of the zeros and the poles such that the steady state error is 0. Or I can have my poles which are very, very close to the origin and so on. Okay, similarly, how do I approximate now not just a derivative, but a proportional plus derivative control? Proportional plus derivative control had a transfer function of the form Kp plus Kd times S. So I can again add a pole and have an approximation now of this form. K over S plus Z over S plus P. And again, we add the pole further away from the origin such that the effect of the pole on the response of the system is minimized. Okay. Now we have a cause controller which is causal, which is stable, and which is less susceptible to high frequency noise. So both the pole and zero are in the left half plane with the pole further away from the origin than the zero. And such an approximation will be called as a lead compensator. So to summarize, we have provided approximations to both PD and PI controllers in the form of lead and lag compensators respectively. What about PID? I can just use the lead and lag in cascade to approximate a PID control action. In the next lecture, we will quickly learn about the integrator wind-up phenomena and then go on to actual design problems using graphical methods or even frequency domain methods and other methods of practical tuning of PID controllers. Thanks for listening.